Welcome to this Kubernetes technical interview questions and answers video. With the rise in containerization, Kubernetes has become one of the most sought out skills for DevOps engineers. So it doesn't matter if you're a seasoned DevOps engineer or just starting up your career, Kubernetes is a non-negotiable skill. But here's the truth. If you're looking to secure a job in this economy, where people are getting fired left and right, you need to be 100% prepared. And as we all know, these DevOps jobs pay a lot of money. I've seen it range from 140K to 300K. So every employer out there is trying to get the best candidate possible. In this video, I'll cover 30 scenario-based questions frequently asked in interviews, and I'll dive deep into each one, giving you an understanding of how these questions should be approached. So sit back, relax, and let's demystify Kubernetes together. Question number 1. I saw in your resume you've been using Kubernetes for the past 7 years. Is that correct? If so, imagine you need to create a Kubernetes pod running on an Nginx container, and you have a manifest file that contains all the necessary specifications. Can you walk me through how you go about applying this manifest file and ensuring that the pods are running as expected? Thank you for asking that question. With my experience working with Kubernetes, here's what I'm going to do. First, I'll start by thoroughly reviewing the manifest to ensure it's correctly defined. I'll check that the API version section is set and that the kind field is set to pod. I'll also ensure that the container image for Nginx are correctly specified. Then I'll verify that the manifest includes necessary configurations such as resource, request, and limits, which I believe are very crucial for pod stability in production. Once the manifest is ready, I'll validate it to catch any errors before deployment. I usually achieve this by running a dry run with the command kubectl apply -dry-run equals to client-f and then the manifest file name. This step simulates the application of the manifest without making changes to the cluster, allowing me to identify any potential issues in advance. Once it's validated, I'll deploy the pod using kubectl apply-f and then the manifest file name. Kubernetes will take care of creating or updating the pods to match the desired states described in my manifest. To ensure everything is running smoothly, I usually run kubectl get pods -oy to make sure that the pods are all in ready state and that there's no error or restart. If there's an issue, I'll immediately inspect the pod details using kubectl describe pods -the pod name to review events or errors. And I'll check the Nginx container logs using kubectl logs space pod name -c space Nginx container name to pinpoint the problem. Next, I'll test the Nginx container functionality by executing a command inside the pods using kubectl exec -it space pod name --curl localhost and column 80. This checks whether the Nginx server is correctly serving content from within the pod. If external access is required, I'll expose the pod using service definitions, either a cluster IP, node port, or a load balancer, depending on the use case. For production readiness, I'll add the readiness prop and the liveness prop configuration to the manifest file to ensure that the pod is healthy and responsive. These props are essential for Kubernetes to manage the traffic routing and automatically restart the container if it becomes unresponsive or fails to start. If there were any performance issues, I'll dive into resource monitoring to check whether the pod is hitting its resource limit. This might involve adjusting the resource request or limit in the manifest to balance workload demand. For further resilience, I'll use horizontal scaling, allowing the pod to scale based on traffic and demand by adjusting the replica count in the deployment. Throughout the process, I'll rely on monitoring and alerting tools like Prometheus and Grafana to continually track pod performance, resource utilizations, and health metrics. This allows us to proactively manage, ensuring the Nginx container is running efficiently and can handle production traffic without issues. Question number 2. Picture a scenario where you have several pods that need to communicate with one another using DNS. Could you walk me through how Kubernetes handles DNS resolution, enabling pods to discover and communicate with each other? Additionally, could you provide an example illustrating two pods effectively communicating through DNS within the Kubernetes cluster? If asked that question, I would say absolutely. Kubernetes simplifies interpod communication by leveraging its built-in DNS system. When you create a pod in a Kubernetes cluster, it automatically gets an internal DNS record, which allows other pods within the same namespace to discover and communicate with it via DNS resolution. At the core of the Kubernetes DNS resolution is the kubedns or core DNS service, depending on the Kubernetes version and configuration. This service automatically runs within the cluster and manages DNS queries for all services and pods. By default, each pod gets a DNS entry based on the name and namespace, with the format podname.namespace.svc.cluster.local. For example, if you had a pod named nginx-pod, in the default namespace, its DNS name would be nginx-pod.default.svc.cluster.local. When one pod wants to communicate with another, it simply performs a DNS query for the target pod's DNS name, and then Kubernetes resolves it internally, routing the traffic through the appropriate service or directly to the pod, depending on how the request is structured. Let me walk you through a practical example. Let's say you have two pods in the same Kubernetes cluster called front end and back end. Both are running in the default namespace. If the front-end pod needs to send a request to the back-end pod, it can simply use the DNS name backend.default.svc.cluster.local. This DNS resolution will route the traffic directly to the back-end pod, ensuring that the front-end pod can communicate with the back-end pod seamlessly. Now, if the pods are behind a Kubernetes service, which is often the case for load balancing and internal communication, the front-end pod can use the DNS name of the service like backend.service.default.svc.cluster.local. The Kubernetes DNS will resolve the service name to the appropriate pod IPs in the backend pod set, allowing the front end to connect to the service, which will then distribute the request to one of the backend pods based on the load balancing and availability. In both cases, Kubernetes ensures that DNS resolution is automatic, efficient, and fully managed, so applications can communicate with each other without needing to hard code IP addresses. The built-in DNS system provides fault tolerance and scalability. Question number 3. Could you share your experience with the types of Kubernetes clusters you've worked with in the past? And have you ever had the opportunity of constructing a Kubernetes cluster from ground up, managing all of its aspects independently? Oh yeah, certainly. Throughout my career, I've had the privilege of working with a wide range of Kubernetes clusters, each with its own unique requirements and challenges. From small-scale single-node clusters for development purpose to large-scale, highly available production environment clusters, I've built and managed clusters in a variety of contexts. In terms of constructing Kubernetes clusters from ground up, I've done so at multiple occasions using different infrastructure setups. Initially, I started with on-premise hardware where I manually configured the nodes, network infrastructure, and storage solutions to support Kubernetes. I've used tools such as kubeadm to initialize and manage the cluster, and then I manually configured networking such as setting up Funnel and Calico for networking and etcd for the distributed key value store. This allowed me to deeply understand the internals of Kubernetes and gave me a hands-on experience in troubleshooting networking and storage issues, particularly in a more complex environment. As cloud-native environments became more prominent, I transitioned to managing Kubernetes clusters in the cloud. I've used and managed Kubernetes services like AWS EKS, Google Kubernetes Engine, and Azure AKS as well, which simplifies a lot of the underlying management. However, I've also built custom clusters using cloud VMs to mirror production-grade environments, ensuring high availability, scalability, and fault tolerance. I've used Terraform to automate provisioning of these infrastructures and Helm to manage Kubernetes packages. One notable project involved constructing a multi-region, multi-cloud Kubernetes setup for a high-traffic application where I had to manually configure the networking and the cluster federation to ensure low latency and high availability across regions. In a couple of other projects, I took the lead on building Kubernetes clusters using bare metal environments, which required configuring everything from the networking fabric to the control plane. This was challenging, particularly around high availability setups, as it involves configuring load balancing for the control plane and ensuring that data persistency is done across nodes. The cluster I set up utilized tools like Metal LD for load balancing and managed persistent storage, which serve for scalability. While I've worked with Kubernetes clusters at various stages of maturity, constructing them from the ground up has given me a comprehensive understanding of the complexity involved in these deployments, especially around scaling, networking management, and ensuring robust monitoring and logging. Additionally, I've gained considerable expertise in automating this task, so I'm always focused in building repeatable, resilient architecture which minimizes manual intervention in the long run. Ultimately, I think the experience of managing every aspect of a Kubernetes cluster, from provisioning the infrastructure to optimizing for performance, security, and resilience, has been crucial to my deep understanding of Kubernetes. Question number 4. Can you explain how Kubernetes handles multi-node clusters? And how would you go about setting up a high available Kubernetes cluster from scratch, ensuring fault tolerance and scalability? Great question. I've had extensive experience managing multi-node Kubernetes clusters, and I'm really passionate about ensuring they're both highly available and scalable. In my previous roles, I've been responsible for building out Kubernetes clusters from ground up, particularly in multi-region environments. One thing I've learned throughout my career is that high availability begins with a control plane. For example, in a recent project where we're setting up the Kubernetes clusters on AWS, I configured at least three master nodes spreading across multi-availability zones, and this ensured that even if one master node failed or an entire availability zone went down, the cluster can still function without disruption. The API server, the scheduler, and the control manager needed to be highly available, so I put them behind a load balancer to ensure that the traffic is evenly distributed across the available control plane and nodes. In terms of the worker nodes, we took a similar approach, deploying them across multiple availability zones. And the idea here was that in the event that an outage happened in one zone, Kubernetes can move to the other working availability zones. This setup not only ensured availability but also made the cluster highly scalable. I used cluster autoscaling to dynamically scale the worker nodes up or down, which, when integrated with horizontal pod autoscaling, allowed us to automatically scale worker loads based on CPU and memory usage. This was particularly beneficial during periods of heavy loads when additional worker nodes were provisioned to accommodate the increased number of pods. For network reliability, I've always relied on CNI plugins like Calico or Weave to handle inter-pod communication. These plugins allow Kubernetes to manage the pod-to-pod networking efficiently, even in a multi-node environment. In one project, I configured Calico for networking policies, ensuring that traffic was allowed only between authorized pods, and I optimized the IP address pool to avoid conflicts as we scaled up and down. This network configuration allowed me to seamlessly communicate between the pods across different nodes, which is essential for multi-node clusters. One of the most important things I've learned when working with multi-node clusters is making sure that critical components of the applications are not all located in a single node. This is where port affinity and anti-affinity comes into play. By spreading the ports across different nodes, I can ensure that if one node fails, the system won't be severely impacted. For instance, in an e-commerce app that I worked on, we used anti-affinity rules to make sure that the database ports were distributed across multi-nodes to prevent a single point of failure. Another aspect of multi-node clusters that is crucial is ensuring that the state of the cluster is protected. In my past experience, we've used etcd for maintaining the state of the cluster, and I've always made sure that it's highly available by running at least three etcd nodes in a quorum configuration. Regular backups of the etcd is also very critical, which is why I implement Velero to take consistent backups of both the cluster state and the persistent volumes. During one incident, Velero helped us to restore the cluster state quickly after an accidental network partition, which minimized downtime. When it comes to scalability, I also focus on building a self-healing architecture. Kubernetes has excellent capabilities for this, so I configure pod distribution budgets to ensure that during node evictions or maintenance, critical services continue to run smoothly. Additionally, Kubernetes built-in health checks such as liveness and readiness props are a game changer for maintaining application reliability across multi-node clusters. If a pod becomes unresponsive or unhealthy, Kubernetes automatically replaces it, ensuring continuous service availability. Overall, setting up a multi-node highly available Kubernetes cluster requires a lot of planning across various components: control plane redundancy, work node distribution, network configuration, scaling mechanisms, and backup strategies. By carefully managing each of these layers, I've been able to create fault-tolerant systems that scale seamlessly in response to the user demand. These experiences have been invaluable in the past, and I'm excited to bring this to your company. Question number 5. In a scenario where you need to deploy a stateful application on Kubernetes, can you walk me through how you use stateful sets and persistent volumes, and also explain the role of persistent volume claims in ensuring data persistency? That's actually an interesting question because at my current role, I just deployed a MongoDB application using Kubernetes, and a huge part of that involved working with stateful sets and persistent volumes to ensure data persistency. When deploying stateful applications like MongoDB on Kubernetes, the primary concern is data consistency and persistence, especially in the events of pod restarting or rescheduling. To address this, we use a stateful set which is specifically designed to manage stateful applications. Stateful sets are unique in the sense that they provide a stable identity for each pod, meaning each MongoDB instance gets its unique and consistent hostname, and more importantly, a stable persistent storage volume that is attached to it. So, if one of the MongoDB pod is rescheduled or crashes, It will be assigned the same persistent volume based on the defined stateful set configuration. For persistent storage, Kubernetes provides persistent volume claims, which acts as a request for storage resources. Once you create a persistent volume claim that specifies the size, access mode, and storage class, when the stateful set is created, Kubernetes would automatically bind the persistent volume claim to the persistent volume that matches the request. This ensures that data is preserved beyond pod restarts. The role of persistent volume claims is to ensure that data persistency is critical. Without persistent volume claims, any data written to the pod's local storage will be lost if the pod crashes or is rescheduled. Persistent volume claims allow you to decouple storage from pods, ensuring that even if the pod itself is terminated or moved, the data remains intact. For MongoDB, we use persistent volume claims to ensure each pod has its dedicated storage, and Kubernetes manages the lifecycle of these persistent volumes automatically. I've had to fine tune this process in my current role to make sure that we're using the right storage classes to optimize both performance and cost, especially when handling large amount of data in our clusters. Additionally, we have monitoring in place to track storage utilizations and alert us whenever we need to scale up storage volumes to accommodate the growing database sizes. In terms of implementation, we define our stateful sets and persistent volumes in our YAML file. Question number 6. Imagine a scenario where multiple pods need to securely communicate with each other across namespaces. Could you explain how Kubernetes networking policies work, and how would you configure networking policies to restrict communication between specific pods? I remember in my first DevOps role, we faced a significant challenge where multiple pods needed to securely communicate with each other across namespaces. The issue arose because we hadn't yet configured proper networking policies to manage this communication, which posed security risk and potential bridges. Essentially, the pods in the different namespaces were able to interact freely, which wasn't ideal for our security posture. To address this, we began by diving into our Kubernetes networking policies. The key thing to understand here is that by default, all pods can communicate with each other across namespaces in Kubernetes, unless you explicitly restrict this access. What we needed was a way to control and secure the communication between the pods, ensuring that only the right services could talk to each other and that traffic was filtered based on namespaces and labels. I started by creating specific network policies to restrict pod communication between the namespaces. For example, we defined policies that allowed only specific services in one namespace to communicate with services in another namespace, ensuring that the communication was secure. A simple networking policy will include rules like allowing traffic only from ports with certain labels or allowing ingresses and egresses from specific namespaces. Once I had the basic policies in place, we ran into an issue where some of the ports that we wanted to communicate couldn't, even though they met the criteria. After some investigation, I realized the importance of defining both the ingress and egresses rules. Most of our issues were resolved once this was done. So I adjusted the network policies to ensure that traffic could flow in and out of the appropriate namespaces and services while still enforcing tight security. Once this was fully implemented, it helped us gain granular control over interpod communication, and we were able to prevent unauthorized access between critical services. This experience taught me the importance of network segmentation and how crucial network policies are in maintaining security in a Kubernetes environment. Question number 7. Have you ever created or managed a custom resource in Kubernetes? Can you explain how you develop a custom resource definition and an operator to manage the lifecycle of a non-standard application in the cluster? Oh yeah, absolutely. I've worked with CRDs in several projects where I needed to extend Kubernetes to manage custom applications. To start with, I would define the custom resource definitions, which allow Kubernetes to understand and manage a new type of resource. For example, let's say we needed to manage database clusters. I would define the CRD to specify the fields like replicas, database type, and storage sizes, ensuring Kubernetes knows how to handle those resources. After that, the real magic happens when I build an operator to manage the lifecycle of these resources. The operator acts like a controller that watches the state of this custom resource and ensures it's always in the desired state. For instance, if the replica field changes, the operator will automatically scale the stateful set to match the new replica count. I usually use the operator software development kit to scaffold and create the operator, which makes things easier by setting up the necessary boilerplates for us. Once that's done, I package the operator into a container and deploy it on the cluster. The operator now continually monitors the state of the custom resources and takes necessary action, whether it's scaling, managing persistent volumes, or other custom tasks. The key benefit here is automation and the reduction of manual intervention, especially for complex applications. In a previous project, I built an operator to automate the database provisioning and scaling, which saved our team a lot of time and reduced human errors. I think having this kind of automation in Kubernetes makes managing large scale applications much more efficient. Question number 8. Could you describe your experience with Helm in Kubernetes? How would you create and manage Helm chats? And what steps would you take to deploy an application to multiple environments with different configurations using Helm? Oh, yeah, absolutely. I've had extensive experience with Helm in Kubernetes, and in fact, I was the one that introduced it to our team. Prior to that, we managed Kubernetes deployments manually using YAML files for each environment, staging, pre-prod, and production. It was very time consuming and prone to errors, especially when it came to making environment specific changes. Every time we needed to modify a configuration or update a service, we had to replicate changes across multiple YAML files, which led to inconsistency and a lot of manual overhead. Seeing how inefficient and error-prone this process was, I took the initiative to introduce Helm to our team. I started by creating the first Helm chart for one of our most critical applications. I worked closely with the team to structure the chart, defining Kubernetes resources like deployments, services, config map, and secrets, all within the chart template. We then externalized environment-specific configurations into a value.yaml file. This way, we could manage configurations for multiple environments with a single Helm chart. The real game changer came when we used Helm's templated system to define environment-specific settings. For example, in production, we could tweak resource limits, replicas, or even specific environment variables in the values-prod.yaml file without touching the core chart itself. This reduced human error, ensuring consistency, and gave us flexibility to handle each environment uniquely with its requirements. After implementing Helm, I also set up Helm repositories for storing our charts, making it easy for everyone in the team to be able to deploy or update applications with simple commands like Helm install or Helm upgrade. Helm's ability to handle versioning and rollbacks was another huge benefit. For instance, if an upgrade introduced a bug, I could simply run Helm rollback to revert the application to the previous stable version, saving us time and reducing the risk of downtime. I also led internal training to ensure that everyone on the team understood Helm's benefits and how to create and manage their own chats. And I believe this knowledge sharing was very crucial as it enabled the whole team to be able to adopt Helm efficiently. Now, we rely on Helm for all of our Kubernetes deployments, and it streamlined our process significantly. By adopting Helm, we reduced deployment times, improved consistency across environments, and made our Kubernetes management much more scalable. In conclusion, Helm didn't just improve our deployment process, it helped drive a cultural shift towards automation and efficiency. It's now an essential tool in our Kubernetes toolset, and I'm proud to have introduced it and helped the team to get up to speed. Question number 9. How does Kubernetes manage resources within pods? And can you walk me through how you use resource requests and limits to ensure efficient resource allocation and prevent a pod from consuming excessive CPU or memory? In Kubernetes, managing resources with pods effectively is essential to ensure efficient performance and avoid overconsumption of cluster resources. The way Kubernetes does this is through resource requests and resource limits. These are specified at the container level, and it helps Kubernetes manage scheduling and resource allocation for each pod. When you define a pod, you can specify both the request and the limit for CPU and memory. The request represents the amount of resources that Kubernetes will reserve for a container, ensuring that the pod gets the minimum amount possible. The limit, on the other hand, is the maximum amount of resources a container can consume. If the container exceeds this limit, Kubernetes will throttle the CPU or potentially terminate the container if it exceeds the memory limits. I've worked on several projects where proper resource management played a huge role in ensuring the stability and scalability of application. For instance, in one of my previous roles, we deployed a microservice architecture where each service ran in its own pod. I set CPU request at 500 M, which is basically half of a CPU core, and memory request at 512 MI. These settings helped Kubernetes allocate just enough resources to run the service, ensuring that the pods couldn't compete for CPU or memory on the node. The limits are just as important. For this example, I set CPU limit at 1 and memory limit at 1 GI. This prevented the pods from consuming more resources than they were allowed, which is crucial to avoid performance degradations or even service outages caused by resource exhaustion. If a pod tried to use more than its memory limit, Kubernetes will kill the pod and restart it, which although disruptive helps maintain the overall health of the cluster. In my experience, this kind of fine-tuned resource management also integrates well with Kubernetes horizontal pod autoscaling. I've used HPA to automatically scale the number of pods based on metrics like CPU or memory utilization. HPA uses resource requests and limits as a baseline to decide when to scale up or scale down. So if a pod is consistently using a high percentage of CPU or memory, the autoscaler can spin up additional pods to share the load. One key point to remember when working with resource requests and limits is to find the right balance. If the requests are set too high, you might end up reserving more resources than needed, which could lead to wasted capacity and inefficient use of the cluster. Conversely, setting them too low could also lead to pod throttling or even crashes, particularly in high traffic environments. I found it extremely helpful using Prometheus and Grafana to track resources usage and adjust them based on the usage. By using resource requests and limits, you also help Kubernetes determine the quality of service for each pod. Pods with both requests and limits will fall into a guaranteed quality of service class, meaning Kubernetes guarantees that the pod will get the resources it needs. This ensures that your application has the resources it requires without competing with other applications in the cluster. In summary, setting resource requests and limits in Kubernetes is a best practice for efficient resource allocation and effective scaling. It's something I've done in multiple environments to ensure that the application runs smoothly without exhausting cluster resources. Through monitoring and adjusting these values over time, I've been able to maintain high performance environments while avoiding costly resource contention. Question number 10. Imagine you're tasked with scaling a microservice-based application. How would you use Kubernetes horizontal pod autoscaling to automatically scale your applications based on CPU usage? Can you also explain the role of custom metrics in scaling? When tasked with scaling a microservice-based application in Kubernetes, I will start by utilizing horizontal pod autoscaling. HPA is built to automatically scale the number of pods in a deployment based on the observed CPU and memory utilization, ensuring that the application remains responsive under varying loads. First, I'll ensure that the microservices running within the pods are configured with resource requests and limits, particularly for CPU and memory. By setting this resource request, Kubernetes understands the minimum resources needed to run a pod. The resource limits define the maximum resources the pod is allowed to use. For example, I might set a CPU request at 200 M and a CPU limit to 1 to ensure that the pod doesn't consume excessive CPU. Next, I'll configure the HPA for the deployment, setting the target CPU utilization, such as 50%. This means Kubernetes will automatically scale the number of pods in the deployment to maintain an average CPU usage of 50%. If the usage rises above the threshold, Kubernetes will increase the number of pods. If it falls below, it will scale down to conserve resources. In some cases, scaling based on just CPU memory might not be sufficient. If the application has specific metrics like response time or request rates that better reflect the load, I'll use custom metrics for autoscaling. For example, I could integrate a tool like Prometheus to collect custom application metrics, such as the number of incoming requests per second or the queue length. Kubernetes HPA can then use these custom metrics to scale based on application-specific demands rather than just resource utilization, giving a more accurate scaling behavior. From experience, I've worked with HPA in production environments where scaling based on resource utilization wasn't always ideal. For example, CPU usage may not spike until a service is heavily overloaded. So by using custom metrics, we could scale up more quickly in response to high incoming traffic or request backloads, preventing service degradation. Overall, HPA combined with resource request limits and custom metrics ensures that the application scales efficiently and that it maintains performance and avoids under or over provisioning of resources. Question number 11. Can you explain the difference between port affinity and port anti-affinity in Kubernetes? And how would you use these features to schedule pods in a way that ensures certain workloads are deployed together or kept apart? Oh yeah, that's an interesting topic. When it comes to pod scheduling in Kubernetes, pod affinity and anti-affinity are really valuable concepts for controlling how pods are placed within a cluster. Essentially, they help determine which nodes the pod will run on based on the pod's location, and you can use them to either group pods together or keep them apart. To begin with, pod affinity allows you to specify rules that ensure pods are scheduled to run on the same node or in the same topology. This is useful when you have services that need to communicate with one another frequently or have low latency requirements. For example, if you're running an application with a front-end service that communicates heavily with a specific back-end service, you might want to place the two services in the same node. On the flip side, pod anti-affinity is the opposite. It ensures that certain pods aren't placed in the same node, which is important for fault tolerance and high availability. A great example would be a scenario where you're running multiple replicas of a stateful service, like a database, for example. If all replicas are placed in the same node, a node failure could cause the entire database cluster to go down. By using pod anti-affinity, you can ensure that these replicas are spread across different nodes so that if one node fails, your service continues to run without complete downtime. I've personally used this concept in my previous roles, especially in high availability setups. For example, at Switch, we were running a critical multi-tier application where we had certain components that communicated intensively with each other. We used Affinity to ensure that these components were placed together on the same node. But we also had a critical microservice that had a single point of failure if collocated with others. For that service, we used anti-affinity to make sure that it was placed on a separate node to avoid a single point of failure. I found that a deep understanding of how affinity and anti-affinity works together can make a big difference in how you manage your cluster resource distribution, especially when balancing performance and availability requirements. Question number 12. Could you walk me through how Kubernetes pod distribution budget works? And in a production environment with critical applications, how would you configure pod distribution budgets to prevent voluntary disruptions from affecting service availability? Kubernetes pod distribution budgets are a crucial tool for ensuring service availability during voluntary disruptions, like when a pod is being drained for maintenance or when pods are being updated, for example. The way I've used pod distribution budgets in the past is to define the minimum number of pods that must remain available even during disruptions. For example, when working on a critical service at my previous job, we had a scenario where we were rolling out updates to a set of microservices running in production. To prevent a situation where too many parts of the same services go down during updates or maintenance, we use pod distribution budgets to ensure that the application will always have a certain number of pods running. To configure a pod distribution budget, I'll first define the desired minimum available replicas used by the min available field. This ensures that if too many pods are being disrupted, the pod distribution budget will prevent the disruption until enough pods are available to meet the requirement. Another key feature is the max unavailable option, where you can specify the maximum number of pods that you can disrupt at any time, helping strike a balance between availability and disruption tolerance. For example, for a deployment of 10 pods where you want 5 pods constantly running, the pod distribution configuration could be passed in the pdp.yaml file, and you can apply this by running kubectl apply-f pdp.yaml. This configuration will prevent the update process from continuing if you resort to fewer pods running at a given time. It's a great safety net to prevent over disruption when scaling or doing rolling updates. In my experience, PDPs are key when you want to ensure that even in cases of failure or node issues, your critical workload continues running without downtime. I've implemented this several times, particularly when working with stateful applications where data integrity and uptimes are critical. Question number 13. Just out of curiosity, have you ever worked with Kubernetes federations before? If so, how would you go about setting up Kubernetes federations to enable cross-cluster workloads and ensure high availability across different regions or data centers? That's a fantastic question. Yes, I've had the opportunity of working with Kubernetes federation in previous roles, and it was instrumental in helping us achieve high availability and resilience across multi-region environments. In that scenario, we're managing a global application that required deployment in different geographical regions to minimize latency and also to ensure disaster recovery capabilities. The primary goal of Kubernetes federation is to allow workloads to span multi-clusters, typically across different data centers and cloud providers, and providing high availability and fault tolerance while doing so. The key benefit here is that if one cluster or region experiences an issue, Kubernetes federation allows you to ensure that your workload remains operational in other regions, ensuring minimal service disruptions. Setting up Kubernetes federation involves a few core steps. First, you will need multi-Kubernetes clusters to set it up, either in different regions or across different environments. These clusters must be able to communicate with each other securely, typically through VPNs or cloud-specific private network solutions. The first step in setting up Kubernetes federation is installing the federation control plane, which includes several components like the API server, controllers, and a sync controller that manages federation resources across clusters. You can deploy this using the Helm chart provided by the Kubernetes federation itself. Once the federation control plane is set up, you will configure it to communicate with the Kubernetes clusters that you want to federate. Each cluster needs to be registered with the federation API server so that resources like services, deployments, and config maps can be synchronized across clusters. A key aspect here is ensuring that each region or data center is represented by a separate cluster in the federation. With the cluster registered, you will start synchronizing resources like config maps, secrets, and deployment across the clusters. This allows you to ensure that your application is being replicated and distributed correctly across regions. For cross-cluster workloads, you typically use the kubefed CLI to manage federated resources like deployments, services, and namespaces. For example, creating a federated deployment will look something like this: kubefed federated deployment, deployment name, namespace equals to namespace cluster equals to cluster name. This will enable the deployment to be propagated across all the clusters registered in the federation. One thing to keep in mind is that the federation helps high availability by ensuring that the workloads are replicated across multi-clusters. However, you also need to consider how to handle things like persistent data because Kubernetes federation mainly deals with the control plane and not necessarily other things like persistent volume across regions. So for stateful applications, you need additional strategies like cross-region storage solutions or replication mechanisms to ensure consistency. From my experience, this setup was critical when working on global scale applications at my previous company. The federation enabled us to distribute our workload to multi-regions, ensuring that users in different geographical locations had low latency access to services. Additionally, it provided failover capabilities, allowing us to ensure uptime even in events of regional failures. Question number 14. How would you secure a pod running a containerized application in Kubernetes? Could you explain the concept of security context? And how would you use pod security policies to ensure security standards for pod deployments? Securing pods is something I've worked on extensively, especially in my previous roles. One of the first things I'll look to when securing a pod running on a containerized application is the security context. For example, in my last project, I had a containerized application that required some additional security configurations. I set the security context in the pod spec to ensure that the container didn't run as root by specifying the run as user field. This is something I always prioritize because running containers as non-root reduces the attack surface. Then there's the pod security policies. I used pod security policies when I worked on a project for a financial institution, which security was top priority for them. For example, we had a policy that denied any container running as privileged or any elevated capabilities. We also restricted the use of host networking and volume mounting, which could potentially expose sensitive data once done. Even though PSPs are deprecated now in favor of pod security admission, they were really helpful in enforcing cluster-wide security settings, especially in that environment. For example, in that same financial project, I also used pod security admission to enforce restricted security profiles on namespaces that house sensitive workloads. This ensures that containers running within these namespaces could not, for instance, use host ports or mount sensitive host paths. Finally, aside from this, I also rely heavily on network policies to ensure communication between pods. In one case, we had pods in different namespaces that I didn't need to talk to each other. So what I did is I used network policies to block traffic between them, ensuring that only the required services had access. Security is always about using multiple layers, and by leveraging security context, PSP, and network policies, I ensure pods are deployed in a way that minimizes any potential risk. Question 15. In a multi-user environment, how would you configure Kubernetes RBAC to ensure proper permissions are assigned to various roles? And can you provide an example of how to create a custom role with a specific privilege for a developer? Great question. I usually advise junior DevOps engineers to begin with a solid understanding of role-based access control in Kubernetes, as it's crucial for securing a cluster, especially in multi-user environments. In my experience, one of the first things we did in teams I worked with was to configure RBAC to ensure that the right people had the right access. For example, whenever we onboard developers to a new environment, we need to ensure that they have access to resources they need to perform their task without giving them too much control over sensitive parts of the cluster. Let's take a common example where we needed to create a custom role for a developer. In this case, we wanted the developer to be able to manage deployments and services, but not have access to delete namespaces or modify other users' permissions. So what I usually do is create a role that specifies exactly what actions the user can perform, such as get, list, and create on resources like pods, deployments, and services. I also used role binding to bind the role to the developer, ensuring that the permissions are granted in a specific namespace, in this case, the dev environment. And this helps prevent the developer from affecting resources in other namespaces like prod and staging. In my last project, I remember we had an issue where one developer accidentally gained permission to delete resources across namespaces because of overly broad access. We resolved this by introducing a more granular approach using RBAC. I advised my team to limit the scope of role bindings and use namespaces to ensure access control remains tight, reducing the risk of accidental disruptions. By strictly enforcing role definitions like this, we ensured that only the right individuals could modify critical resources, while everyone else stayed within their authorized scope. Setting up RBAC this way really helps maintain security, and it's one of the first things I focus on when onboarding new team members. I've also seen a big improvement in collaboration because everyone knows exactly what they can access and modify within the cluster. Question 16. Can you explain the role of kubelets in node management? And how would you ensure that nodes are healthy and that Kubernetes can effectively schedule workloads across them, especially in a large-scale production environment? The kubelet is the primary agent running on each node in the Kubernetes cluster. It's responsible for ensuring that the container in the pods are running as expected. It watches for changes to the pod definition and ensures that the containers are started, restarted, and maintained according to their desired states. To ensure node health and efficient scheduling of workloads in a production environment, I focus on several aspects. First, I ensure that the kubelet's health checks such as the readiness and liveness props are correctly configured for both the nodes and the containers. This allows Kubernetes to understand when a container or a pod is becoming unhealthy and needs to be restarted without causing downtime to the overall application. I also rely heavily on monitoring tools like Prometheus and Grafana to track key metrics such as CPU, memory usage, disk I/O, and network traffic across the nodes. By setting up alerts, I can ensure that if a node starts becoming unhealthy, we are notified right away and take appropriate measures to make sure that it doesn't cause a significant disruption. In large environments, I use tainting and toleration to manage workloads better. If a node is under heavy loads or having issues, I taint the node, ensuring that only critical workloads that tolerate the taint will be scheduled on it. This prevents non-critical workloads from affecting the node's performance. Additionally, I've also worked with node affinity and node anti-affinity to ensure that workloads are distributed evenly across available nodes, and certain workloads are scheduled together or apart based on specific rules. For example, placing database ports on nodes with SSDs to ensure optimal performance. Lastly, I monitor the kubelet log closely. Any abnormalities or failures in the kubelets can lead to issues with scheduling and pod management, so I always make sure that the logs are being collected and analyzed for any warning signs. In short, ensuring that the nodes are healthy and that Kubernetes can schedule workloads efficiently across them involves proper configuration of the kubelet, leveraging resource management features, and setting up monitoring to identify issues early. Question 17. How do you set up centralized logging and monitoring for a Kubernetes cluster? What tools and frameworks would you use to gather, analyze, and visualize logs and metrics from the Kubernetes environment? In a Kubernetes environment, centralized logging and monitoring are crucial for ensuring the health of a cluster, debugging issues, and optimizing performance. Over time, I've worked with several tools and frameworks, and I'll walk you through how I approach setting this up. For centralized logging, I usually recommend an AFK stack, which consists of Elasticsearch, FluentD, and Kibana. FluentD acts as a log collector and a forwarder, which collects the logs from all the containers and sends them to Elasticsearch for indexing. Elasticsearch is a power search engine that allows for efficient querying and filtering of logs. Finally, Kibana is used for visualization of logs in an easy-to-read format. It allows you to create dashboards that help you visualize the logs and track application health. I ensure that FluentD is set up as daemon set so that it runs on every node in the cluster. FluentD is then configured to collect logs from the Kubernetes pods, nodes, and system components like the kubelets, scheduler, and controller manager. By forwarding all this data to the Elasticsearch, you have a single source of truth for all your log collection, making troubleshooting a lot more manageable. For metrics monitoring, I typically use Prometheus and Grafana. Prometheus is a powerful time series database that pulls in metrics from all Kubernetes components such as nodes, pods, and services, using its well-built-in scripting capabilities. I'll set up Prometheus as a deployment in the cluster using Service Monitor to scrape metrics from various Kubernetes endpoints like kubelets and kubelet API server. To enhance this even further, I often use the Prometheus adapter for exposing custom metrics and scaling the application based off these metrics. Grafana is typically used to visualize all of these metrics, and Prometheus collects the data. For example, I could create a Grafana dashboard to monitor pod resource utilization such as CPU and memory consumption, to track if any workloads are resource heavy. Another important aspect of monitoring is alerting. I integrate Alert Manager with Prometheus to handle alerting. If certain thresholds like the CPU usage are breached, or if a pod goes down, I set up rules to alert the DevOps or the deployment team via Slack or email. Lastly, for monitoring application performance and tracing, I often use zipclean for distributed tracing. This tool allows you to track requests as they move across multiple microservices, helping pinpoint the bottleneck and failure in the application. Integrating this tool with Prometheus and Grafana gives a comprehensive picture of both the infrastructure and the application level performance. Overall, with EFK for logging, Prometheus and Grafana for monitoring, and tools like Alert Manager and Jipper for performance tracking, I can ensure that we do not only have detailed observation of the Kubernetes environment, but also the ability to quickly act if any issue arises. Question 18. Describe your experience with upgrading a Kubernetes cluster in a production environment, and what steps did you take to ensure zero downtime and avoid disruptions throughout this process? Upgrading a Kubernetes cluster in a production environment is a delicate process that requires careful planning, execution, and testing to ensure zero downtime and maintain service availability. Let me walk you through an approach I've taken in the past when upgrading a cluster and ensuring smooth transition. Firstly, pre-upgrade preparation is critical. I always begin by reviewing the Kubernetes release notes to check for any breaking changes or deprecated features that could affect the current setup. It's also essential to evaluate the impact on running applications, particularly if there are any custom configurations or third-party integrations that could be impacted by this upgrade. I work closely with the development team to review the potential impacts and get a consensus on what needs to be upgraded. Next, I typically back up all critical data and configuration, such as etcd and the Kube API server configuration. Ensuring that a reliable backup is available allows us to roll back in case something goes wrong. I also ensure that the cluster's persistent volume claims and important secrets are backed up. This provides peace of mind whenever we want to do an upgrade. For the upgrade process itself, I prefer taking the rolling update approach. This means upgrading one node at a time, starting with the master node followed by the worker nodes. I upgrade the master node first to ensure that the control plane remains functional during the process. After upgrading the control plane, I test it to ensure that it's fully operational and that the core services like the API server, controller manager, and the scheduler are functioning as expected. Once the control plane is stable, I proceed with upgrading the worker nodes. I use the rolling upgrade strategy with the kubectl drain command to gracefully evict pods from each node before the upgrade starts. Once the node is upgraded, I mark it as schedulable again, and Kubernetes will automatically reschedule the pods on the remaining nodes. I keep an eye on the application performance and health metrics through Prometheus and Grafana throughout this process. One crucial consideration during this process is ensuring the compatibility between Kubernetes versions and the application workload. I use Helm to manage deployments as it helps ensure that the application configuration and charts are compatible with the new Kubernetes version. I also test the upgrade in a staging environment before executing it in production. By replicating the production environment in staging, I can simulate the upgrade process and identify potential issues beforehand. Any changes made to the custom configuration, RBAC policies, or network policies can be tested here to avoid any surprises. Lastly, after the upgrade is completed, I closely monitor the Kubernetes cluster and the application workloads for the next few hours to ensure that everything is running as expected. I look for any signs of performance degradation, memory leaks, or failed pods. If there are any issues, I rely on the backup and restore process, including rolling back the upgrade if necessary. By using a systematic approach that involves backups, rolling upgrades, and proper testing, and even continuous monitoring, I've been able to upgrade Kubernetes clusters in production environments with minimal disruptions, ensuring that the application remains highly available throughout this process. Question 19. Can you explain how Kubernetes ingress controllers work and how they interact with services to provide load balancing and route traffic? What are the considerations you always have in mind when configuring an ingress controller for production environments? That's a great question. So at a high level, the ingress controller in Kubernetes acts as an entry point for both HTTP and HTTPS traffic into the cluster. It manages how external traffic is routed to different services inside the cluster. The ingress controller typically works by evaluating the rules set by the ingress resource, which defines how requests should be directed to the backend services based on this URL paths and host names. Now, one of the core features of the ingress controller is load balancing. It helps distribute incoming traffic across available ports for a given service. This ensures high availability and scalability at the same time. For example, if you had multiple replicas of a pod running a service, the ingress controller will route requests to the different pods in a round robin fashion or based on other algorithms like the list connects or depending on whatever setting you have in place. In terms of configuring ingress in a production environment, there are several key considerations I focus on. First, high availability is crucial. To make sure that the ingress controller itself is resilient, I usually run multiple replicas of the controller to avoid single points of failures. It's also important to ensure that there's an external load balancer in front of the ingress controller, especially in cloud environments. For on-premise environments, we might use something like Nginx to serve as a reverse proxy. SSL/TLS termination is another important factor. In production, securing communication between the client and the service is a must, so we typically configure the ingress controller to terminate SSL. A tool like Cert Manager can be integrated with the automated SSL certificate manager, making sure that the certificates are always updated. I also make sure that proper routing rules are defined in the ingress resource, like path-based routing or host-based routing. This way, we can direct traffic to the appropriate backend services depending on the URL or the host. For instance, traffic coming from myapp.com/API might go to one service, while myapp.com/auth goes to another. Lastly, monitoring and security are crucial when configuring ingress in production. I rely on tools like Prometheus and Grafana for monitoring the performance of the ingress controller and the traffic it handles. On the security side, I configure things like IP whitelisting and rate limiting to protect us against DDoS attacks and ensure that only the trusted resources can access the services. Question 20. How does Kubernetes handle pod restarts, shutdowns, and live events? Thank you for that question. The pod lifecycle in Kubernetes is a well-defined process that Kubernetes manages from the moment a pod is created until it's terminated. The lifecycle of a pod is governed by its pod spec and can be impacted by various factors like resource usage, health checks, or failure states. Let's break it down step by step. When you first create a pod, whether it's manually or through a deployment or stateful set, Kubernetes schedules the pod onto an available node based on the resources available and constraints specified in the pod's configuration. Once scheduled, the kubelet on the node starts the containers inside the pod. During this initial phase, Kubernetes ensures that the pod is running as expected. If a pod is unable to start or a container inside the pod fails to launch, Kubernetes will attempt to restart the container or the pod based on the restart policy that's defined, which could be always, on failure, or never. For instance, if a pod fails, Kubernetes will try to restart it to maintain the desired state as per your deployment specifications. Now, when it comes to graceful shutdowns, Kubernetes handles it by sending a seek-term signal to the container, allowing it to gracefully shut down. By default, Kubernetes will give the pod a window of time, the termination grace period seconds, to shut down before it forcibly kills the pod with a seek kill signal if it hasn't exited yet. This is critical, especially for applications that need to clean up resources or gracefully close connections. For example, a web server gracefully closing active requests. Pod restarts also come into play during failure scenarios. Kubernetes tries to be intelligent here. For example, if a container crashes, it will attempt to restart the container and give it a fresh state. However, if a pod is continuously failing, for example, due to an application bug or resource constraints, Kubernetes will eventually mark the pod as unhealthy, and it can trigger alerts or scale up/down based on the deployment strategy you've defined, such as a rolling update. As for health checks, I'm a strong believer in setting up readiness and liveness probes for every critical service in Kubernetes. The liveness probe checks whether a pod is still running and should be restarted if it's not healthy. The readiness probe checks if the pod is fully initialized and ready to start accepting traffic. These checks are essential to ensure that the application can continue running, and if a pod becomes unresponsive or stuck, Kubernetes can automatically take it out of rotation before it causes issues with production traffic. For example, in my previous role when managing a microservices-based application, we used readiness and liveness probes extensively. There was one instance where we had an application running on a pod that started to consume excessive memory due to a bug. The liveness probe quickly detected the pod was unhealthy and caused it to restart automatically. The application then recovered quickly, and we were able to patch the bug without any major downtime. Finally, during the pod's termination phase, once it's marked for termination, Kubernetes will ensure that any pod-associated resources are cleaned up. It's important to note that if you're running a stateful set or need persistent storage, you should have persistent volume claims, PVCs, properly configured, as the volume should persist beyond the pod lifecycle. When the pod is terminated, the volume may be detached,
but it will not be deleted, ensuring that your data is protected. To summarize, the pod lifecycle in Kubernetes involves several stages: creation, running, health checks, termination, and cleanup. And Kubernetes makes sure that each phase is handled in a way that ensures high availability and minimal disruption to service. By configuring things like restart policies, graceful shutdowns, and health checks properly, we can make sure that applications remain resilient and reliable in production environments.
Question 21. How does the Kubernetes scheduler decide where to place pods within a cluster? Can you walk me through how you can customize the scheduler with affinity rules, taints, and tolerations to optimize pod placement? Great question. The Kubernetes scheduler plays a central role in deciding where a pod gets placed within a cluster. It looks at available nodes in the cluster, checking whether they have enough resources, like CPU and memory, to meet the pod's resource requests. The scheduler also takes into account things like node constraints, available labels, and the pod's affinity or anti-affinity rules. These help the scheduler make an informed decision about where to place the pod based on how resources are utilized and what the overall requirements are. When it comes to customizing the scheduler's behavior, I've used a few features in the past, including affinity and anti-affinity rules, along with taints and tolerations. For example, affinity rules are really useful when I want certain pods to be placed together. In my previous role, we had a scenario where I wanted to make sure that certain pods, like those running related services, were always scheduled on the same node. This can help with performance, especially when you have services that need to communicate quickly. On the other hand, anti-affinity is perfect when I need to keep pods apart, like when I'm deploying a multi-replica application and I want to ensure that no two replicas of the same pod are placed on the same node. This helps maintain high availability. Then there are taints and tolerations, which give you another level of control. For example, I once worked with a set of nodes in the cluster that had high performance GPUs, and I wanted to make sure only certain pods, like those running ML models, were scheduled on those nodes. So I applied a taint to those nodes, which essentially marked them as special and only allowed specific pods with matching tolerations to be scheduled there. In a practical scenario, I would first define which pods should go where, using affinity for related services, anti-affinity for replicas, and then apply taints and tolerations to ensure that workloads with specialized needs get the resources they require. This kind of fine-grained control is especially useful in a production environment where I need to ensure both performance and availability across the entire cluster. Question number 22. Have you ever had the opportunity of integrating Kubernetes with a CI/CD pipeline? If so, can you describe the steps you took to automate the deployment process of the application, ensuring consistency and reliability across multiple environments? Definitely. Integrating Kubernetes with a CI/CD pipeline is something I've worked on extensively in my previous roles, and I think it's a game changer for ensuring streamlined and reliable deployments. One example that comes to mind is when I was responsible for automating deployments for a microservices-based application at my previous company. We had several environments, such as dev, staging, and production, and our goal was to make sure that each environment was consistent and that we could deploy seamlessly. To begin with, we use Jenkins as the CI/CD tool, but I've also worked with GitLab CI and GitHub Actions. We configured the pipeline to trigger automatically on commits to our version control system, Git in our case. The first part of the pipeline would build the application and run unit tests to ensure the code is stable. Then, we would containerize the application using Docker, which is pretty standard for Kubernetes deployments. The next step was to push the built Docker image to a registry, like Docker Hub or Amazon ECR. From there, I used Helm to package and manage Kubernetes deployments. We stored the Helm charts in a version repository and made sure that each environment, dev, staging, production, had its own set of configuration values. So we could easily tweak things like resource limits, image tags, or environment variables. After that, we used kubectl commands to deploy the Helm charts to the appropriate Kubernetes cluster based on the environment. In the case of more complex deployments, we would use tools like Argo CD or Flux for GitOps style deployments, where changes to our Git repository would automatically trigger the pipeline, ensuring that the Kubernetes cluster reflects the desired state defined in our code. To ensure reliability and consistency across environments, we automated testing in our pipeline. This included both unit tests as part of the build process and integration tests in the staging environment. If a test failed, the pipeline would stop, preventing an unstable application from being deployed. In production, we ensured zero downtime by using rolling updates in Kubernetes.
This allowed us to incrementally roll out new versions of the app and easily roll back if something went wrong. Overall, the goal was to maintain a smooth, automated process with minimal human intervention, while also providing visibility into the pipeline's performance and catching issues early. The consistency came from using version controlled Helm charts, automated tests, and environment specific configuration.
Question number 23. Have you ever developed a custom scheduler for Kubernetes? If so, can you walk me through the reasons you will build a custom scheduler and how would you implement it to address specific scheduling requirements in your environment? Yes, I've worked on customizing Kubernetes scheduling, though I haven't built a scheduler from scratch. However, I can explain the approach I would take if I needed to. Typically, you'd consider a custom scheduler when the default Kubernetes scheduler doesn't meet specific requirements. For example, if you need to schedule workloads based on unique criteria like GPU allocation, network bandwidth, or even custom business priorities, a custom scheduler is a great option. It's also useful in multi-tenant environments where workloads need strict isolation or when certain workloads have SLAs that require prioritization. To implement one, I'd start by clearly defining the requirements, what's missing in the default scheduler, and why it's necessary to go custom. Then, I'd evaluate whether an extender or scheduling plugin might be sufficient, since those integrate seamlessly with the existing scheduler and save development effort. If a fully custom scheduler is the best route, I'd leverage the Kubernetes scheduling framework. This involves building custom logic in Go to handle predicates, priorities, and binding decisions, and then deploying the scheduler as a pod within the cluster. Finally, I'd ensure robust testing, observability, and failover to avoid disrupting production workloads. This approach ensures the custom solution is well targeted, maintainable, and aligns with Kubernetes best practices. Question 24. Can you explain how Kubernetes metric servers function in the cluster? And how would you use it to monitor pod resource consumption and provide input for horizontal pod autoscaling?
That's a great question. The Kubernetes metric server is a core component used to collect resource usage data from the nodes and pods in your cluster. It's not a full-fledged monitoring tool like Prometheus, but it's lightweight and focuses on gathering metrics related to CPU and memory usage, which are essential for scaling decisions. The way the metric server works is by scraping the kubelay on each node for resource metrics like CPU and memory utilization. These metrics are then aggregated and stored in the metric server, which can then be queried via the Kubernetes API. This data is not stored long-term, which makes the metric server ideal for real-time, current resource usage metrics rather than historical data. For horizontal pod autoscaling, HPA, the metric server plays a crucial role in providing the necessary metrics to drive scaling decisions. The HPA monitors resource utilization, usually CPU or memory, and adjusts the number of pods running based on those metrics. By default, the HPA uses the metric server to determine the average CPU usage of the pods it's monitoring. If the average CPU usage exceeds the defined threshold, for example 80%, the HPA will trigger a scale-up event to add more replicas. If the usage is low, it will scale down. In terms of how I've used it in the past, I typically configure the metric server first by deploying it into the cluster, which can be done via kubectl apply f using the metric server YAML manifest. Once it's running, I can query the metrics with the kubectl top command like kubectl top pods or kubectl top nodes, which gives a live view of resource usage across the cluster. Once the metric server is running and metrics are being collected, I would then configure the horizontal pod autoscaler to scale based on these metrics. For example, if we're dealing with a stateless service that needs to handle more traffic, we might configure the HPA to automatically scale the pods based on CPU utilization. If I set the HPA threshold to 75% CPU utilization, once the average CPU across the pods exceeds that threshold, the HPA will increase the pod replicas to handle the increased load. In the past, at my previous job, we had a highly dynamic service where the load could spike unpredictably. Using HPA alongside the metric server allowed us to automatically adjust to those load spikes without manual intervention. This really helped maintain application performance and stability while optimizing resource consumption.
Question number 25. How would you approach selecting and configuring a network plugin for Kubernetes? And what are the advantages of using specific container network interfaces like Calico or Weave in different use cases? That's a really good question. When selecting a network plugin for Kubernetes, I always start by understanding the specific requirements of the environment and the application workloads we're running. Network plugins, or CNIs, provide the networking capabilities that connect containers and pods, so it's crucial to choose the right one based on factors like performance, security, scalability, and ease of management. For example, in a scenario where you need high performance and fine-grained security control, I would lean towards Calico. Calico is known for its speed and scalability, and it also provides network policies, which are key for ensuring security within the cluster. In one of my previous roles, we had a microservices-based architecture with hundreds of services, so isolating traffic between different microservices was important. With Calico, I was able to implement network policies that allowed us to restrict traffic between specific pods and namespaces, making sure that only the necessary services could communicate with each other. It also integrates seamlessly with Kubernetes network policies, which is a huge advantage if security is a priority in your environment. Another use case where Calico excels is in large-scale Kubernetes clusters, especially with cloud-native network functions, CNFs. I remember at my last job, we were managing a production-grade Kubernetes cluster with several nodes in multiple regions, and Calico provided the flexibility we needed in terms of setting up advanced routing and handling pod-to-pod communication across different regions. On the other hand, Weave is more suitable for simpler use cases where you need quick and straightforward setup without too much overhead. It's a great option for teams that may not need the advanced features of Calico, but still want a reliable, stable networking solution. Weave is also a good choice if you're dealing with smaller clusters or want to set up networking in an environment that doesn't require complex policy management. I used Weave in a development environment where simplicity was key, and it worked great for managing pod-to-pod communication without requiring complex configuration. When configuring a CNI plugin, I would first assess whether we need features like network segmentation, pod security policies, or the ability to support multiple networks within the same cluster. For instance, with Calico, I would enable the Calico Network Policy Controller to enforce fine-grained control over pod communication and ensure that all traffic between pods is encrypted, especially if sensitive data is involved. I'd also make sure that the plugin supports the required network topologies, whether that's a flat network or a more segmented one. In summary, the choice between Calico and Weave largely depends on the scale and security requirements of the environment. If I need strong network policies, scalability, and flexibility, I would go with Calico. If the environment is simpler with fewer security concerns, Weave would be an excellent choice. Both of these CNIs are widely adopted in the Kubernetes community, and I've found both to be reliable depending on the use case. Thank you for sticking with me through this video. To wrap things up, I'll be sharing the last 4 questions that are frequently asked during interviews. If you'd like a Word document with the detailed answers, feel free to leave a comment and I'll send it your way. Question number 26. In a situation where your pod fails to start, can you walk me through your troubleshooting process in Kubernetes? What commands would you use and what logs would you check to ensure that you resolve this problem quickly? Question 27. Can you explain the different storage options available in Kubernetes, such as persistent volumes, stateful sets, and dynamic provisioning? And how would you manage stateful workloads requiring high availability and performance? Question 28. Have you worked with Istio or any other service mesh solution in Kubernetes? If so, could you walk me through how you implement Istio to manage microservice communication, observability, and security in a Kubernetes cluster? Question number 29. How do you usually audit and assess the security of your Kubernetes clusters? Can you explain the tools and best practices that you use to ensure that the cluster is compliant with security best practices and that you're identifying vulnerabilities? And finally, question 30. Could you explain the Kubernetes API service role in the control plane and how authentication works within Kubernetes? How do you implement API service access control and integrate external authentication systems like LDAP or OIDC? If you enjoyed this content, please subscribe to the channel. We've got an exciting live troubleshooting session for Kubernetes coming up soon, so stay tuned. You won't want to miss it.